If this was the size of the sun, how small would it have to be to make a black hole? Hi, this is Keely, and the question is, if the sun got crushed down and became a black hole, which it can't do, how big would it be? Well, our sun's going to end up a white dwarf. Smaller than that, it's a neutron star. That's where everything kind of collapses together and you just get a density about equal to what's in a nucleus. If you squish it down even further, and we don't even know what the mass is then, or what really is, because it's not what we call mass anymore, it becomes a black hole. If our sun was to do that, how big would it be? Well, on this scale, this is Jupiter. Would that be the size? No, too big. This would be the size of the Earth. Right there. No, too big. How about the end of this? Now that's more like it. So let's do the physics and figure out how big we have to crush the sun down to become a black hole. Our sun actually can't do this, but for the sake of argument, let's say it can. So if we view our sun, let's say the sun is here, and the planets are making little ellipses inside that gravitational well created by our star. Let's say that was actually to continue to collapse. Now our sun can't do it, but let's say it was able to collapse and become a black hole. What would happen? Well, as far as our picture here is, if the sun collapsed, this well would elongate and narrow to the point where at some point all that mass is compressed in a volume small enough that it now becomes a black hole. In other words, it reaches what's called the Schwarzschild radius, which is the radius of the event horizon of a black hole, roughly. And so let's see what we need to do. Well, first of all, we need to figure out how deep of a hole that we've got ourselves dug into when that collapses down. So to figure that out, we need to figure out how deep that gravity well is. So depending on which one's your favorite symbol, usually PE, a lot of people think about that near Earth as just MGH, but we're talking about bigger than that outside the Earth. So we're going to use this, negative G M1 M2 over this is the mass of the sun, mass of the other object, and the distance out to that object, in which case usually it's the radius that we're talking about, or from, in this case, the sun out to wherever it gets squished down enough. G is 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. And we need to figure out how fast we need to go, how much energy that we need to climb out of that well. And so that's energy of motion, which is kinetic energy, which is 1/2 mv squared. So to actually figure out the size of the sun, if it was to crush itself down and become a black hole, which again, it can't, it's not massive enough, what we've got to do is we've got to climb out of that hole. So we've got to get all this out. So we have to take that potential energy plus the kinetic energy, and that's got to equal 0. We've got to have enough kinetic energy to climb out of that potential well. So if we plug things in, we get negative G, because again, it's a hole, mass of the sun in this case, mass of the other object, divided by R, plus 1/2. This is the mass of the object, so it's M2 times its speed squared. So I want to move this over to the other side. So we get G M1 M2 over R equals 1/2 M2V squared. And the M2's cancel, which is nice. Now, for this to become a black hole, that means that that escape velocity has to be greater than the speed of light, which is 3 times 10 to the 8th meters per second. So I want to use that as my limit right here. We're going to figure out how much it's got to squish down. So this would be the minimum size that the sun will have to be. And I want to go ahead and solve for R, but let's hold on to that for just a second. So let's go with, actually, I will go ahead and move it over. So we get 6.67 times 10 to negative 11. The mass of the sun is about 2 times 10 to the 30th kilograms, equals 1/2 v, which is 3 times 10 to the 8th, that's the speed of light, squared r. We got to solve for r. So I'm going to go ahead and move the other stuff over. So we get 2 times that 6.67 times 10 to the minus 11. I should have kept this in more symbols. That way I wouldn't have to write as much. To the 8th squared equals r. So let's throw that into my trusty calculator here. So we've got 2 times 6.67 times 10 to the negative 11 times 2 times 10 to the 30th divided by 3 times 10 to the 8th squared. And we get that our radius for the sun to squish down and become a black hole is 2,964 meters, which is about 2.96 kilometers, or about 3 kilometers. So the sun will have to squish itself down to the size of just 3 kilometers radius for the sphere in order to become a black hole. Again, it can never do that, but that's how small you have to go to squish the sun down and make a black hole. Thanks for watching, and please like the video, and if you liked it, please subscribe. Thank you. Bye.